All right, we are in unit number 6, conservation of energy, and to be frank with you, this is probably the most important law in all of science. Any of our conservation laws, conservation of momentum, conservation of energy, these are the laws that scientists use to govern their thoughts as they work through science. And so this is of all the conservation laws, conservation of energy is one of the biggest ones out there. So big stuff today. All right, so we're going to start you off with a key concept with conservation of energy, and then work you through a term called system. Make sure you understand what a system is. I'll give you the definition to conservation of energy, and then the next video we'll do an example. So here we go. Key concepts, conservation of energy, page 5 of your notes. Scientists consider conservation laws to be the most important laws in all of science, and that's what we just talked about. When we talk about conservation laws, and specifically conservation of energy, we always need to be aware of what's called the system. And let me give you the definition first, and then we'll run through a couple examples of systems. So it's a defined quantity of matters. So you can define it any way you want. In a way, it's arbitrary. You can say the room that you're in is the system. You could say, if you're working in a petri dish, you could say the petri dish and its contents inside there is the system. If you want to talk about the Earth, you could talk about the Earth as a system. You could talk about the universe as a system, or the solar system as a system, or a particular experiment that you're doing as the system. So you can define it pretty much any way you want. So it's a defined quantity of matter enclosed by either real or imaginary boundaries. Examples. Real boundaries would be like the walls of this room. There's a ceiling, there's walls, I can touch those. Those are real boundaries. When we talk about imaginary boundaries, would be like the solar system would be our system. Well, there's no wall that contains the solar system. So in that case, the boundaries would be more or less imaginary. We would imagine that they're there, even though they're not really there. Okay, any set of objects can be considered a closed system as long as they do not interact, and I guess the emphasis here is on closed, as they don't interact or exchange. So when we talk about interact, we mean interact is exchanging energy with objects considered outside the system. So you can define a system any way you want, but it doesn't necessarily mean that that system is going to be closed. Closed being that energy is either removed from that system or energy is absorbed by that system. So you can define it any way you want, but if it's receiving or giving energy from its environment, then it's not a closed system. Still a system, but it's just not a closed system. So within a closed system, particles can exchange. Okay, we call that transferring. Exchange energy with each other, but must have absolutely no interaction with anything outside the system. And that's for a closed system. The largest closed system that we have is going to be the universe. Okay, there's, as far as we understand, the universe, which is basically everything that God created, no energy goes in and no energy goes out. And we can call that a closed system. I gotta sneeze for a moment. Let me turn the mute on. And then the Earth, is the Earth a closed system? Down below. Well, technically it's not a closed system. And the source of energy that the Earth receives from its environment would be the sun. The sun gives light to the Earth, and that's a form of energy, in that the sun is outside of the Earth, and so it's outside the system. If you define the system as the Earth, and so the Earth is receiving energy. So the Earth itself is not a closed system. So we would say no, and we would say sunshine. All right, the next one, we have conservation of energy. This is a 19th century definition. Energy cannot be created or destroyed. All right, so why did we put 19th century definition in there? We put it in because over the last 100 years, especially right around the early part of the 20th century, the whole idea of conservation of energy drastically changed. I'm going to tell you about that change as we move along through the chapter. Up until the late 1800s, early 1900s, our idea of conservation of energy was what you see here in this definition. It was energy cannot be created, energy cannot be destroyed. That worked up until the early part of the 1900s, or the early part of the 20th century. When Einstein came along and came up with relativity, he changed the way we think about energy, and especially the way that energy is conserved. And he said, and I'll give you a little bit of a preview right now, he said that energy it can be destroyed, and it can be created. If you destroy energy, you create mass. And if you destroy mass, you create energy. So both mass and energy can both be created and destroyed, and if you destroy one, you create the other. It's like two sides of the same coin. Well, we're not going there right now. So let's hold off on that idea of creating and destroying energy till later on in this chapter. Let's just work with the idea that, or work with basically a 19th century definition of conservation of energy, because it'll work really well for what we're going to be doing in the classroom. And then later this chapter, we'll go ahead and open it up to a 21st century definition, or a 20th century definition. All right, so here it is. Energy cannot be created or destroyed. And what does that mean? It says the amount of energy in a system remains constant. And actually, I would say the amount of energy in a closed system will remain constant when no work is done on or by the system and no energy is transmitted to or from the system. So if there's no energy being transferred to or from the system, by definition, it's going to be closed. Another way of thinking of a conservation of energy, the total energy of an isolated system is constant. Isolated is kind of a word that means closed as well. And then the last one, energy can be transferred. Transferred means exchanged among objects within a system and still preserve the law of conservation of energy. All right, now that was a lot. But I would say for right now, the one you need to worry about is number one. Just the fact that energy cannot be created or destroyed. And we're going to use that as we move through the rest of these topics. And there it is. We'll start with example number 2, an example of conservation of energy on the next video.